All right, so now let's look at the binary selector. So here is basically a quick way to execute the left or the right child based on a condition task. So it doesn't currently have anything assigned. So let's say we'll do seek player or random patrol. So we want to do one of these. Now what you'll notice is that unlike the previous ones we've used, we cannot drag an additional entry from here, an additional output. Because it's a binary node, it can only have two connected out nodes. Now you see here it says no task, because you can put a condition task directly in here. So in our case, we're going to do is active, and we're going to check that against our door. So here you see if the door is active, he's going to do the random patrol points. If the door is inactive, he's going to seek the player. So again, right click, set that as the start. So he's seeking the player. We turn the door on, random patrol point, seek the player, turn the door on again. And because the door's currently on, he's going to do the random patrol points until the door is off. He finishes the patrol point, now he seeks the player. So that one is very straightforward, just true or false. Now this also has the dynamic, so I can turn dynamic on, and now it will evaluate that condition there. You see he will immediately change to seek or to patrol. And it looks very smooth and responsive. Now what you'll notice is that I can actually add multiple conditions. So here I can assign another condition task. So let's say check target within distance, connect that to our player. So if our player is less than 15, and here we go, if all true, if the door is active and the distance is less than, so actually, in this case, let's do any true. So if any of these are true, so if the distance is less than 15 or the door is, and let's change this to be if the door is not active. And what we can do is we can actually just change the order of this. And you see, when I change the order, it immediately changed from true to false. So I move this over here, and this becomes true. So now if any of these are true, so if the door is inactive, or the distance is less than 15 to the player, we're going to seek the player. Otherwise, we're going to randomly patrol. So there he's randomly patrolling. The distance is greater than 15, so he's not able to get to me. But when I move over here, he's now going to try to seek me because I am less than 15, even though the door is not open. And of course, we can change this to be all true. So now if the door is not active and the distance is less than 15, so you see the door is open, but his distance was not. Now it is, because he came within range of that patrol point. There we go. So he patrols there. He's patrolling up here. Comes down here. Now, as soon as he comes towards this patrol point, like now, he's going to switch to seek because he sees me. And of course, if I turn the door on, he's just going to start patrolling. So that looks really great and works really smoothly and is very clear to read here. All right, so let's have a look at the next one, the Priority Selector. So right click, set it as the start. All right, so this one will execute the child with the highest utility weight, and if it fails, it will go to the next highest utility weight and keep going until one succeeds or they all fail. So similar to how a normal selector works. And each child branch represents a desire, where each desire has one or more considerations which are considered together. So considerations are a pair of input value and curve, which together produce the consideration utility weight. So let's have a look at that. So quite a wordy one, but let's make some connections. So let's say we have a similar thing here. So seeking the player and randomly patrolling and seeking, so going to the middle. So we have these three here. Now you see, as I connect them in, it creates these here. And I can actually click this. So it's different to the node. you click this on the actual node connection itself, and it comes up with a connection inspector where I can change the friendly name and I can add a consideration. So right now we have a weight of nothing and we want to add weights to this. So let's add a consideration. So let's say for seeking the player, we're going to put an input in here, and our input here is going to be a value. So we need to add something onto our Blackboard variable, so a number. So let's make a float. Okay, so let's say we have an aggression float, how aggressive they are. Let's make another one, which is how hungry they are. So now, if they are hungry, we put that in there. If they're aggressive, we put the aggression one in there. And now what we need to do is we need to create a curve. So you just press that to create the curve. And now the curve can be linked to a variable as well, but let's just do it in here for now. And let's just use a basic curve. So we'll do these two. And what you'll see is that as I change this value, okay, which means that we want to do 0.2 aggression and like 1 hunger, okay? So here what you can see is that because he has hunger maxed out, then this is higher priority. And let's just run this and see how it works. So what I'll do is I will expose these to be public so that I can modify them here. Yep, there we go. So now I can just scrub them up and down. So let's start them off at 0. So right now he's seeking the player. He's chosen to seek the player. If I increase his hunger, now he's prioritizing going to there. If I increase his aggression, he goes to seek the player. But what you'll notice is that when he's neither aggressive nor hungry, so when they're both at 0, he's still doing seek player or go to the center, which is not ideal. So what we can do here is we can add the consideration here, and we'll input the hunger and add another consideration and input aggression, and we're going to create a curve, and we're actually going to inverse this curve. So in order to do that, we can either inverse the curve directly here, or I can just do 0, 1 to 0, like that. So what you'll see is now when you look at these values here, 0 for our desired 0, which is, let's just give it a friendly name. I'm hungry, I'm angry, and I'm not hungry or angry. And as we adjust these, so let's say we put our aggression and hunger to 0, you see our average here turns into 1. And that means that this is going to be higher weight and this is going to be selected. So let's play it and see what happens. Let's get rid of that door again. Okay, so as you can see, he's neither aggressive nor hungry, so he's just going to patrol around. Now we're going to increase his hunger a little bit. We'll keep going. And there we go. So past 0.5 hunger, he's going to actually go and seek the middle of the playfield. Now, obviously, this is a very simple example, and what you would rather do is have a bunch of different variables, maybe their HP value. So you can factor their HP value into it. You can factor how far away they are from the player, how many times the player has attacked them, all sorts of things like that. And so, you know, for example, here, I'm angry, I'm aggressive. We could add HP, we could add how many times they've been hit by the player, and we could add maybe like a general random aggression value for the monster or for the enemy. And again, with this one, we can make it dynamic so that as these values change, it updates more immediately. So there he goes. And actually, let's make a nice example here. So I'll add a consideration, and I'm going to create a new variable in the graph. And this is going to be called HP, and it's going to start at 1. We're going to create our graph, and we'll just make it linear to be simple. Input 1, input min 1, input max 0, because we want it to not contribute to the aggression when it's at 1. That means we've got full health. And when we have 0, we want it to contribute here. Okay, so now we have a general aggression value, and we have an HP value. I'm going to expose that to be public. So down here, we have HP starting at 1. All right, so right now, he's randomly patrolling He's randomly patrolling. He's neither hungry nor angry. He's completely fine. Now I'm going to increase his hunger to 1. So now he wants to go towards here to eat. And what I'm going to do is I'm going to reduce his HP to 0.2. We now have the angry at 0.4. And our aggression currently is 0. So let's say we set it to 1 because the player hit him. Now it turns to 0.9. But his hunger is still more than his desire to attack us. So let's say he gets to that point there. Okay, so he's there. And let's say he's eating. So now his hunger goes down. And now he's aggressive because his aggression has now outweighed the hunger that he has had. Great. So let's move on to the next one, Probability Selector. So again, we'll just right-click, set it as a start. So the Probability Selector is going to select a child to execute based on its chance to be selected and return success if the child returns success. Otherwise, it's going to pick another child. And it's going to fail if all the children return failure or a direct failure chance is introduced. So this is going to randomly select something to do. So let's use our same examples here. Copy these over, connect them up. And you see, as I connect them up, it's actually giving me a percentage here. It's giving me a 33% for all of them. It's going to evenly split them. Now, let's say I want him to do the seek player very rarely. I can click that connection there. Again, not the nodes, but the connection itself. And I can reduce that. So let's say I give it a weight of 0.5. So now this has a 20% chance to happen. And the others have a 40%. Or let's put it even lower. So 0.2 weight. Now this has a 9% chance to happen. And if I add another node, so I'll just copy paste this, you see it will recalculate all the probabilities automatically. So it's very convenient. And if you click here, you can actually change the weights here as well if you want, so you can see them all together. And you can link those weights up to a variable if you need to. And here, you can also introduce a direct failure chance. So we could say there's a point, and this is a weight as well. So there's 12% chance that it will just completely fail. And I'll delete this, and everything will just update automatically. So now there's a 31% chance that it's going to fail. So let's make that lower. So there's an 8% chance that it will fail, and there's also an 8% chance that it will do the seek player. So let's see what that looks like. All right, so he's chosen to seek the middle. Now he's chosen the random patrol point and seek, and he will most likely do those. Now he's actually chosen seek player. And he's going to keep doing these. They have higher weights, so it's more likely they're going to happen. There we go. He's got that rare chance to seek the player. So that works pretty great. In this case, if it did do a direct failure, it would actually go back and reevaluate because we have it on repeat. So it would not have exited. Now, of course, this still works perfectly fine with our other examples. So if I copy these over, so I want to grab these, and we're going to make sure that we're only going to seek the player when these conditions are passed. Okay. And what I will do is I will give it a really high weight. So 60% of the time, he's going to seek the player if he can. 30% of the time, he's going to randomly patrol. And the other 10%, he's just going to go to the middle and kind of reset. So let's see it. All right, so the door was open, so he was able to seek the player. All right, and he's going to keep doing that, and that's the one that's most likely. So after he finishes that go to middle, he's basically going to go back and seek that player. All right, so now I'll turn the door on, and you see here, because it fails, he's going to go to the next one. But then as soon as those conditions pass, he's going to favor seeking the player because it has a higher percentage, like that. So let's have a look at the step sequencer. So the step sequencer, in comparison to a normal sequencer, which executes all its children until one fails, the step sequencer executes its children one by one per step sequencer execution. The executed child status is returned regardless of success or failure. So what does that mean? So if we take our normal sequencer here, I'll copy it over, And I'm going to copy these nodes and put them underneath the step sequencer as well. So in the case of the sequencer, what it's going to do is it's going to go through in order from the very beginning to the end. And as soon as the child returns failure, the sequencer will stop. So it goes through here. Let's say our door is inactive, then it's going to return fail, and it's not going to run these. However, with the step sequencer, it's going to go into here. Whether the door is active or not, it doesn't matter. It's going to return up here. Then in the next tick, it's going to go here. Then again, it doesn't matter if it succeeds or fails. It's going to go back, and then it's going to do seek player. So let's play and see what that does. So our door is actually active here, which means that this is going to fail. So it fails here. We step forward, and you see it's actually playing this. In a normal sequencer, it would not have gone here. Whereas in the step sequencer, it's going to do the next one regardless of succeed or fail of the previous one. All right, so let's set up an example that will make it more clear what's going on. So what I'm going to do is I'm going to add a parent sequencer like this. Right-click, set that one as the start. And now what I'm going to do is I'm going to either seek the middle or do a random patrol. And that's going to happen every time this comes through. It's going to choose the first one the first time. And then the second time, it's going to choose the second one. And then over here, I'm actually going to create another sequencer here. And that's going to be our standard checking if the door is inactive and the player is active. Connect these up like that. And so what's going to happen is it's going to go into here. First, it's going to do a random patrol. Then it's going to seek the player if it can. Then it's going to come back here and it's going to go to the middle of the screen, the middle of the game scene. Then it's going to seek the player again if it can, and then continuously do that. So let's have a look. So right now, let me just turn the door off. So right now, he's doing the random patrol point. Then he moves into here where he's going to seek the player. And when he finishes seeking the player, he goes back to the start. And this time, instead of the random patrol points, because it's in a step sequencer, he does the next action. He does the action after the one that he did last time. He does the seek, go into the middle. And of course, if we turn that door on, he's just going to continuously go between these two because this is going to fail. Great. And now let's have a look at the last composite node, the switch composite. So the switch will execute one child based on the provided int or enum case and return its status. So this is a useful node to create state-like behaviors. So here you can see our selection mode right now is index-based. And let's drag these in. So we're going to use the same nodes here. Copy paste. There we go. And you can see we have 0, 1, and 2 assigned to each of these connections. Make sure we set it as start. And you can see the current is 0. And so if I play this, he's going to do this basically forever until we change his int case. So let's say I change it to 1. Now he's going to do this. And he's going to keep doing this because our current value is 1. And we're setting it basically explicitly. It's not checking any conditions outside of anything else. So the idea of this is that you can pass in a state that maybe you've created yourself, and it can switch behaviors based on that. So in this case, we were just using an integer, and that, of course, can also be connected to your graph. So I could create this here, int case, and let's just call it state, for instance. Again, expose that to be public, look at our enemy, click this, and now I can change it there. So in this case, the 0 state is the aggressive state, and the 2 state is the hungry state, where he goes here to eat something, and 1 is the patrol state. Now, it's not really great that we're modifying it kind of manually like this and having to remember which each of these are. So what we can do is we can use an enum instead. So here, instead of index-based, we can change it to be enum based, and we want to create a new enum. All right, so now when we create an enum, we can actually choose, these are all reflected types. Now, obviously, these are not really useful for us. These are mainly internal enums used by either NodeCanvas or other plugins or Unity itself. So let's create our own enum. So we're going to create that in code. So I'm just going to create a new script. Let's go call it my enum. But you can imagine with an existing code base, you would already have certain enums around the place. All right, so I open this up and I'm going to create a public enum monster state, and that's going to be idle, aggressive, hungry. And that will move it outside of the class, so it's just there. Okay, so there we go. We have our enum, our monster state enum. All right, let that compile. Okay, and what we want to do here is we want to connect that up. So now when I press null and I search for monster state, it comes up. It's reflecting it from our code. And I simply click that. And now what you can see is that we have our idle, aggressive, and hungry all right here. Now, hungry is right, but aggressive and idle are wrong. So how do we fix this? Well, we simply change the order. We move this over here, and that becomes linked to idle. That's because it's doing it in order of the enum. Idle is first in the enum, therefore the first node that's connected to this will use idle. And if I have an extra one here, you see it tags as never. So that's telling us that's never going to happen because there's not enough states in our enum for this to happen. If we were to now go into our code and add a new state, which is scared, we save, wait for it to compile. Now you see, automatically it has been connected to scared. And so let's say scared, we're going to do flee. So we will change this. So instead of moving there, I will delete that seek and I will do flee. Connect that to our player, connect our speed variable up as well, the distance to flee at. So say 5. All right. And let's just check our enemy. So you see here, we need to expose our enum case and we can delete that old state. So I'll delete that state there. I will expose my enum case. So let's just say monster state. There we go. So we have a nice enum selector there. Now when we play, he's going to do the random patrol because he's an idle, as you can see here. Now I'm going to change this to be aggressive, and he's going to seek the player out. There we go. Now I'm going to change him to be scared, and he runs away from the player. And you see we set him to run away until 5 units. And if we change that, we could change it to be like 20 or something. And there, he's going to run a lot further away. And as we chase him, he's going to keep running away because he's scared. Then I flip that. He's aggressive again. Now he's chasing us. Now he's hungry. So he's going to go to the middle, just like that. And we can also make these dynamic so that he reacts more instantly. So it means that when the enum changes, he's going to change immediately to the next state. And same here, if one of these conditions fails, then he's going to fail this immediately rather than waiting for this to finish. So let's have a look. So he's going to do the random patrol points. Now I change him to be hungry and immediately he goes there. I change him to be aggressive. All right, he's coming at me there. I change the door to be off. And now you see he is aggressive, but because the door has failed, he's not going to do anything. He's aggressive, but he can't do anything. And that's because we are controlling it via the state. We don't have any additional conditions here. But for the sake of this example, it makes sense. All right, so that's an overview over all of the composites of NodeCanvas. The sequencer, the selector, the parallel, the binary selector, priority selector, probability selector, step sequencer, and switch. All of these, which can be used in combination with each other to make really compelling and complex behavior for enemies or other AI in your game. So hopefully this tutorial helped you understand how each of these work, as well as use cases for all of them. And hopefully you can use NodeCanvas to create much more compelling and believable behaviors for the AI in your games.